I'm looking at a dataset with two features, age and income. The age ranges from 18 to 65, and income ranges from 20,000 to 150,000. This is one of the features in my dataset. Its values range from a minimum of 18 to a maximum of 65. Pretty straightforward, right? The other feature in my dataset is income, with values ranging from 20,000 to 150,000. This represents a wide income spectrum. This is a scikit-learn tool I use to standardize my data, making it easier to work with. It centers the data around 0 and scales it to have a standard deviation of 1. This is the dataset after I apply the standard scaler. The mean of each feature will be 0, and the standard deviation will be 1. But important to note, the shape of the data doesn't change. It's like shifting and stretching the data, but it retains its original form. I'm presented with multiple choice questions testing my understanding of how the standard scaler affects the dataset. I need to identify the true statements about the transformed data. The overall goal is to understand how applying the standard scaler transforms the original dataset. We'll analyze the impact on the mean, standard deviation, and distribution shape. It's all about how the transformation changes the numbers, but importantly not the underlying patterns. I'll explain this one first because it's straightforward. Standard scaler works by first centering the data. That means it subtracts the average from each data point. So, after applying standardscaler, the new average of age and income will be 0. Pretty cool, huh? Next, let's talk about the standard deviation. This measures how spread out the data is. Standardscaler also divides each data point by its standard deviation. This makes the new standard deviation of age and income equal to 1. Here's the thing about standardscaler. It only changes the mean and the standard deviation. It doesn't change the SHAPE of the data's distribution. If the age and income data wasn't normally distributed before scaling, it won't become normal after using standardscaler. I see that you're asking about statement D. This statement is true because standard scaler works by subtracting the mean and dividing by the standard deviation. That means I apply the same scaling factor to every data point within a single feature. This keeps the ratios between the data points identical. Think of it like zooming in on a picture. The things stay proportional. If point A was twice as far from point B before scaling, it will still be twice as far from point B after scaling. Let's check statement C. This is false because standard scaler only affects the mean and standard deviation. It doesn't change the shape of the data. So, if your data was skewed before scaling, it will still be skewed afterward. I'm not changing anything about the distribution's shape. Now I'll explain statement B. It is true. Standard scaler divides each data point by its feature's standard deviation. That's what makes the standard deviation of each feature equal to 1. After I'm done, statement A says that the mean of both features will be 0. I tell you, it's true. Standard scaler subtracts the original mean from each data point. That neatly centers each feature at 0. I'm going to explain how standardscaler affects the dataset. Think of standardscaler as a data pre-processing tool that makes your data more uniform. It's like giving your data a makeover before you use it in a machine learning model. This is one of the features in our dataset. It represents the age of individuals, ranging from 18 to 65 years old. This is the second feature, showing income levels that vary from 20,000 to 150,000. This is a function from the scikitlearn library in Python. It's used for scaling numerical data. I use it to standardize data, which means I change the data so it has a mean of 0 and a standard deviation of 1. It's a crucial pre-processing step for many machine learning models. After I apply standardscaler, the average, mean, of both the age and income features will be 0. That's a key effect. Similarly, after scaling, the standard deviation, a measure of how spread out the data is, for both features will become 1. It means I've made the spread of data consistent. Important note here. Standardscaler doesn't magically make the data normally distributed. If the data was skewed before, it'll likely still be skewed afterward. Standardscaler only affects the mean and standard deviation. Here's a cool thing. Even though I'm changing the mean and standard deviation, the relative distances between data points within each feature stay the same. The relationships between data points are maintained. I'm working with a dataset that has two features: age, ranging from 18 to 65, and income, ranging from 20,000 to 150,000. This is one of the features. The values for age are between 18 and 65 years old. This is the second feature. Income values are between 20,000 and 150,000. I'll use the standard scaler from scikit-learn to preprocess the data. This is a technique that standardizes the data. Standard scaler transforms the data so that each feature has a mean, average, of 0 and a standard deviation, spread, of 1. After applying standard scaler, the average of both age and income will be 0. This is true. After applying standard scaler, the spread, standard deviation, of both age and income will be 1. This is also true. Standard scaler doesn't change the shape of the data's distribution. It only changes its mean and standard deviation. So, if the data wasn't normally distributed before, it won't be after. This is false. The distances between data points within each feature remain the same relative to each other after applying standard scaler. Think of it like zooming in on a map. The relative positions of things don't change. Only the scale does. This is true. I'm looking at how standardscaler changes a dataset with age and income features. I want to understand the effects on the data's characteristics. This is a function from the scikit-learn library. It's used for data preprocessing, specifically to standardize numerical features. It does this by centering the data around a mean of 0 and scaling it to have a standard deviation of 1. After applying standardscaler, the average, mean, of both age and income will be 0. This is because standardscaler subtracts the original mean from each data point. The spread, standard deviation, of both age and income will be 1 after using standardscaler. This happens because standardscaler divides each data point by the original standard deviation. The distances between data points within each feature, age and income, stay the same relative to each other. Although the scale changes, the ratios between differences are constant because the transformation is linear. I'm scaling everything equally using the same scaling factor for each feature. I'm working with a dataset containing information on age and income. Think of it like a spreadsheet with two columns, one for people's ages and one for their yearly income. I'll use the standardscaler tool from scikit-learn, a popular Python library for machine learning. This tool helps me prepare the data for my machine learning model. The ages in my dataset range from 18 to 65 years old. And the incomes range from $20,000 to $150,000 per year. After applying standardscaler, the average age will be 0, and the average income will also be 0. Pretty cool, huh? The standardscaler also makes the standard deviations of both age and income equal to 1. That means the spread or variability of the data is standardized to 1 unit. Even though I'm changing the average and spread of the data, standardscaler keeps the relationships between data points the same. If one person's income is twice another person's, that will still be true after applying standardscaler. This shows the result of standardscaler on the age data. The average becomes 0, and the standard deviation becomes 1. Similar to age, this line shows the result of standardscaler on the income data. The average becomes 0 and the standard deviation becomes 1.